Let's move on. We're talking about overall broadcasting. So now it's time to discuss a question. When we network based on switches, its actual network range is very small. The scope of the broadcast is under a broadcast domain. Then it is actually a network segment. Or, when we learn VLAN in the future, dividing VLANs will also have different webcast domains. So the network segment is not accurate. Let's just say it's a broadcast domain. Then it stands to reason. For example, now I have a broadcast data frame. Purpose MAC all 1. Written in hexadecimal is all F. Is a broadcast frame. I can flooding in the second layer network. Then the largest area of flooding is a broadcast domain. Now communicate based on the second layer. Only within this range. ARP we learned in the last lesson. It is a broadcast. This data is sent to the router and it is gone. Data forwarding is not possible. Then if you want, data goes from this device to this device. Now if the data gets here, if only communication within the broadcast domain is used, this data is impossible. We're going to pass the routing function. Just like the cross-network segment access I mentioned just now. As long as the host finds that the source IP and destination IP are not in the same network segment, it is now the process of finding the gateway. Is in the process of routing. This is the same. Data is now going from a broadcast domain to another broadcast domain. Then it is impossible to communicate directly. Must rely on the routing function of the router to help us communicate. So this will involve the concept of routing. Today I will simply explain these pictures around. When a data reach this router, RA. When the data comes, each layer of data is encapsulated. It first needs to see if the purpose MAC is looking for it. If not, it discards. The principle of the second layer is, first check whether the target MAC is for yourself. Deal with it if it is. If it is a broadcast, also handle. If it is a multicast, also handle. After watching the second floor, just look at the third floor. For example, data is going to this router, RD. Then RA will think about it now. RD wants RA to help it forward data. It's going to find this router. But RA doesn't know where this router is now. Unable to forward data for RD. If possible, RA will help it. If not possible, then RA will discard the packet. What we said. Is there any information about the destination network segment? We call it. Is there a routing entry to the destination network segment? We will focus on this routing entry today. Before talking about routing, let's review the simplest data. Two devices. They are on the same network segment. We call such a device connection as direct connection. Then the future network. Certainly not all devices are directly connected in pairs. In the future, there will not be only two adjacent devices for data communication. It's not that once the device is crossed in the middle, it's not a direct connection. The communication between them will rely on the function of routing. Because it is directly connected, they can communicate directly. This is the first concept we covered. The concept of routing. So if there will be multiple devices in the future, the data is going to the destination network segment. After passing through other routers along the way, then the data is sent. Will be on this router. To query a local representation. Routing table. According to the route 1 by 1 in the routing table. Direct data forwarding. This is the concept of the routing table. Now any layer 3 device. It doesn't have to be a router. It can also be a layer 3 switch. Firewall. All okay. The third layer refers to the network layer. In the future, when addressing and forwarding, Forwarding based on destination IP addressing. Addressing. We will query the routing table of the device. Data forwarding based on routing. Specific addressing. The specific address forwarding is based on routing. So let's see what the routing table looks like. This is what the routing table looks like on a Cisco device. No need to check every time the routing table is displayed. For this thing, enter show IP route on the device and it will come out. This is one of its commands. Let's take a look at the above part first. These are some code names. You don't have to watch these every time. For example, if you want to see this route, in front of this there is an O. You don't know what this is. Look up. This O stands for OSPF. This C stands for connected. This is one of my direct connections. That is, this thing is a reference table. Just to save some characters of numbers. So no need to watch it every time. Here is the routing table. Then in this table, there are a few important points that need everyone's attention. OSPF we will talk about in NA. Connected we will also talk about. D stands for EGRP. We will also talk about this. L stands for local. S stands for static. These 5 are the ones we will be exposed to at this stage. Let's take a look at the contents of this table. First look at the first line. You don't need to pay special attention to this kind of thing. This is a collection of main class subnets. This 1.0.0.0 represents a subnet. Actually, you don't need to read this line. When we learn data to guide forwarding, don't need to pay attention to this thing. Let's look directly at the next line. This is the real routing entry. Let's parse a routing entry now. Let's look at this one. This is a piece of information in the routing table. I just said, this O stands for OSPF. This data is learned through OSPF. Learned means automatic. We'll get to OSPF in a minute. It is a dynamic routing protocol. Now this position of O. It is used to identify what protocol is used to form the destination network, or how the destination network is formed. It is now formed through the OSPF protocol. Okay. I annotate it. This is O. Then look down at 1.1.1.1. This is the destination network. Now this network and this route go to 1.1.1.1. I will give you a simple example. For example, there is now a routing table on this device. There is a route tune in it. Is 1.1.1.1. Then if there is a data in the future to RB here, it is going to 1.1.1.1. It happens that there is 1.1.1.1 in the routing table. You can help it forward accordingly. If the purpose of RA is to go to 1.1.1.1, but there is no 1.1.1.1 in the routing table, then this data is discarded. So this is called the destination network. Then everyone will notice. It writes 1.1.1.1 here. Its form seems to be different from the network segment. Can you see it? Students? It seems to be different from the network segment. It seems to be going to such an IP address. Everyone will find. This is an exact IP address. It is not an expression of a network segment. Here you will see 12.1.1.0 bar 24. Those with a bar 24 on the back represents a network segment. For what we say now, the bar 24 means it is in the 12.1.1.0 network segment. These are the two forms of routing. That is, classification of routes. In terms of its scope, there are two types of routes that appear in the routing table. Segment routing. Network segment routing is the network number. Network segment plus mask. This form is called network segment routing. There is also a route called host route. What we see now. It is a very standard host route. It is an exact host address. This is called host routing. Then this route can only represent one address. And 12.1.1.0 represents the entire network segment. Let me explain the difference. For example, this is a routing table on a router. This is a router. A data is sent to this device. Going to 12.1.1.3. Then please pay attention. It can match this route. Then send it out through the 1.0 interface of the current device. But for 1.1.1.1, it represents an exact IP address. If a piece of data is to be sent to 1.1.1.1, can help forward. If data is to be sent to 1.1.1.2, there is no corresponding route here. Just don't forward. So the network segment covers 12.1.1.0. That is, in fact, all addresses from point 1 to point 254 can be forwarded. This is called segment routing. This is the routing table we're talking about. Some basic concepts of it. This is called the classification of routes. Okay. Let's move on. Here is a 110.2. 110 refers to the administrative distance of the routing protocol, followed by a 2. It's called routing metric. Routing metrics are also called cost. It has many names. And then there is a via. 12.1.1.1. This is the address of the next hop. Let's take it as an example. For example, now a piece of data has arrived on the RB device. The data is going to be the address of this interface on the destination router. Now query the routing table to find. It has the address to the destination router. So RB will help with data forwarding. Then when forwarding, need to specify the destination IP of the next hop, because it involves future requests to ARP. That is, after this data is sent out, which interface address should be sent to. This is what we call the next hop. It's just that after this data is sent to the left interface of the router. That is, the left interface of RD. This is called the next hop. The interface that the data needs to arrive at when leaving the router. The address we call the next hop, or the address to be reached. The places marked in yellow represent different parameters. Look down. Here is a 000059. Let me tell you this briefly. You don't have to remember. This refers to the time when the route was learned. It's not important to us at this stage. Further down there is a fast Ethernet. This is the fast Ethernet port. Ethernet is a common 10M interface. Fast Ethernet is a 100M interface. Its bandwidth will be larger. Then in here, F10 is an outgoing interface. That is, now when this data goes out, go out from an interface of the device. This data is sent to the next hop address. Which interface should the device send out to reach the next hop? The number of this interface is the outbound interface, called F10. This is the full picture of the overall routing table. I'll make a supplement to you. There are two ways to form the next hop address. The first way is to manually specify. This method is called static routing. We will learn dynamic routing later. That is, we can use the agreement, automatically generate the next hop for it. This is called dynamic. We'll talk about the difference between the two. I now ask you a question. There is now a routing table. Why sign the protocol? For equipment. As soon as the data arrives on the device. Is there a 1.1 like this? Why do you have to identify it? How was it learned? Does it have anything to do with the overall learning process? I'll give you a simple example. For example, there are now 3 devices. Connect them first. Assuming that the routing table of this device is, there are 2 same routes. If there is a 12.1.1.0 now, 30-bit mask. This is a local direct link. But for this device, I can also configure some static routes on the device. Like now, the device learned a route through the direct connection. Also via 12.1.1.0. Also a 30-bit mask. A route is also written in a static way. Then this is the local direct route. That is, this 12.1.1.0 network segment is a local directly connected network segment. But now I have written a static route. I can artificially configure an address to 12.1.1.0. Such a static route. Now the device on the left goes left. That is, if it believes in this direct connection, it will go left. This device comes out of this interface. This is its next hop. If it believes this static, go right. The device comes out of this interface. This is its next hop. Then for the same entry network, equivalent to having 2 directions. If there is a data in the future, match this 12.1.1.0 30-bit mask. Does it go left or right? Here comes the problem. Everyone must be clear. Routing has a principle of adding tables. Optimal addition table. We will compare the priority of forming this route. That is, compare its administrative distance. If the current administrative distance is as small as possible, the device will believe the small. Actually, for different routing types, there are different learning styles. Management distance is not the same. Assume that the left side is directly connected. Static on the right. If it is directly connected, in this table it shows connected. Then its overall administrative distance is 0. For the right, this static administrative distance is 1. Now for the same destination network segment. Now the device only trusts this direct connection. It will add table. While static it does not add table. Although they are learned through different routing protocols. But sometimes you may have doubts. As long as you learn it, isn't it all right? Why do you have to define it? How did you learn it? Because of different learning styles. Its administrative distance is different. If there is a direct connection and a static, then we will choose direct connection. Because direct connection is definitely the fastest. Is it connected under the interface? But please be careful. Routing protocols and administrative distance. For devices from different manufacturers, they are different. That is, if the 2 routes we just talked about also appear, then only one will appear in the routing table. It's the direct connection on the left. This is the principle of addition. Compare the priority values of the formed routes. The smaller the value of the administrative distance, the better. Winners will be added. Relatively inferior will be eliminated. That is, it will not enter the routing table. This is the first question. Let's move on to the second question. For us now, our scene changed. Now change the right side to a 24-bit mask. We now have 2 options. Now both sides are also going to the 12.1.1.0 network segment. The one on the left is directly connected to the one on the right that is static. Then it stands to reason. Definitely better. So we now have to choose. If the future appears in the routing table, do you think it came up? Or does it appear? Or both? Because this is a 30-bit mask. Represents fewer hosts behind. Go left. I have now written a more general. Go right. Which do you think it is? Okay. Both should be added. Assume that the address on the right is not listed. Now both sides are 12.1.1.0. Don't look at the mask. It stands to reason that direct connection is better than static, because it manages a shorter distance. Now comes a data. This data went to 12.1.1.5. Then 12.1.1.0. 30-bit mask. Variable host bits only have the last 2 bits. Actually its range is 000111011. Then remove a network address and a broadcast address. It can actually use 2 addresses. One is point 1. One is point 2. It does not cover point 5. But point 5 is included in the network segment of the 24-bit mask on the right. If you don't understand what I'm saying, that means when I talked about subnetting before, you may not have a good grasp. Need to review after class. To us. In fact, it is covered in the following network segment. If this route has not been added to the routing table just now, that means the data is coming. Just discarded. Obviously the data can arrive, but not retweeted. This misses an address. So for the data, although the part before it is the same, but it masks differently, means it is a different network. Please pay attention. The same network must have the same network number. And the mask is the same. Same destination network. So as long as there is any difference between the two, then it is not the same network. It is a different network segment. All the different network segments need to be added to the table. If the destination network and mask, if the information is inconsistent, we'll add table. If inconsistent, we'll trigger the comparison. Comparing administrative distances forming routes. It is a triggered comparison. We'll have the following comparison. Then we mean. The consistent situation refers to the destination network plus mask is exactly the same. So let's formally discuss administrative distance. It will not happen that the direct connection is on the left and on the right. For example, there is now a direct. It is going to 10. 1.1.2. 30-bit mask. Assume that this router interface can only be configured with 2 addresses. Either point 1. Either point 2. This means that an address is occupied here. Then the address on the right. It is impossible to have the same network segment as it. So it can't be a direct connection. That is, under the 2 interfaces of the router. It is impossible to have addresses in the same network segment. It cannot be both directly connected. So our drawing is also very rigorous. It is a static. Can be configured manually. We can guide the flow. The original data arrives at the destination network segment. This may be a direct connection to the device. But we can then do some bootstrapping. For example, go to other network segments. So, both are directly connected. There is no way to achieve it. Then the addresses under the 2 interfaces will conflict. There is now a router with a routing administrative distance. For administrative distance, I hope you remember a word. Locally effective. The administrative distance is for a single device. Why is it locally effective? Because the future is in the overall project. You tend to see multi-vendor device combinations. That is, it is impossible for all devices to be from the same manufacturer. This situation will not exist, because it will involve the safety rating of the project site. It is impossible to use the same manufacturer's equipment. In case there is a bug in its bottom layer. In case it is now system unstable. In case there is a problem with this batch of network equipment. Then the whole project is paralyzed. Therefore, It is often used in combination with multi-vendor equipment. And by cost-effective. So you will see. All kinds of equipment are used together on site. For example, here is a Cisco device. Then on the Cisco device, when I am doing local routing calculations, it is calculated according to your own management distance. If the right end here is another manufacturer's equipment, then it is different from Cisco. That is, for equipment, network equipment from different vendors, the definition of administrative distance is different. So there is no way to compare. Only valid for this device. They made some agreements with each other. Then when calculating, do calculations locally. But don't worry. We have a very large number of routing protocols compatible with multi-vendor devices. It does not vary by manufacturer and device model. This leads to problems with the routing table, although the definition is different. But the final calculation results are almost the same. Unless you are in the NP stage in the future. We'll learn some problems that introduce each other. In the NA phase, only remember the local effective administrative distance is to compare the optimal route on the router. Only manage this device. Can't manage other equipment. Okay. Next we will have another concept called cost. For now, you will see marked with an OSPF on it, marked with an EGRP underneath. On behalf of the RA now through a different routing protocol, can learn the route 10. 1.1.0 on RB. If let this router choose, it will definitely choose to go down. Let's look at the form below. EIGRP has a smaller administrative distance. For equipment, it thinks smaller is better. That means OSPF learns this and doesn't want it. But it's not like you don't want it completely. It will be kept as a spare on the device. Actually it's just unlisted. But this information is still stored locally. If sometime in the future, maybe the following device interface is broken, then based on such a dynamic routing protocol, RA soon sensed that the following path could not be taken. It was originally under the letter and then walked down. But the following device produces a failure. There is a problem with the link. Then go up. This route will be added to the routing table immediately. For data forwarding, it is a spare. That is, if EIGRP fails, OSPF will be added to the appearance. Then go this way on a daily basis. If it has a problem, take the above path. Let's move on to the next scene. For example, now it is not through direct connection. Instead, it is learned through OSPF. Then for OSPF, in Cisco, the management distance is 110. Actually, management distance is also divided into internal and external. I wrote this called external administrative distance. Don't need everyone to master now. Now the device passes the left and right. All learned a 12.1.1.0 route. And all learned through OSPF. The principle of adding tables to routes is, if the destination netmasks are inconsistent, add them to the table. Trigger comparison if it matches. Comparing administrative distance. But now the embarrassing place is administrative distance consistency. Because it's all learned through the same protocol. Admin distance is 110. Now both routes need to add table. We will now have some new parameters. Can come to provide a control. Routing metric. That is the cost we just talked about. So now you will find the same destination network segment. And they come from the same protocol. When learning the same way. Can't compare now. Then we can only choose to compare the new parameters again. Compare route metrics. The route metric represents the A cost when the routing protocol forms this route. The smaller the cost, the better. You should know. Different protocols have different calculation methods. So what we're talking about cost. It only makes sense to compare under the same protocol. So if we now compare the administrative distance, when can't compare, we will compare its cost. We look at this picture. They go to the same network segment. How can such a graph be formed? Data should go through this interface. I want to go through this interface again. How can such a picture be achieved? Let's take a look. Now all routes are learned through OSPF. All devices run OSPF. Still a route. Judge or RA. Now the above learned one through OSPF. The following is also learned through OSPF. Then it is now going to the same such a network segment. There are two roads. In theory, you can choose both ways. OSPF is also relatively consistent. At this point we will compare a value called cost. The route metric. It's also smaller. Above is now 20. 10 plus 10 equals 20. Below is now 2. 1 plus 1 equals 2. This 10 refers to the cost of the interface. And OSPF calculates the cost of the outbound interface that sends the data. Make an accumulation. Now the top is 20. Below is 2. Then the following will be selected. That is, choose the one with a small cost value. Data will go like this. When comparing under the same agreement, we'll compare its cost value. If the management distance is the same, we'll compare routing metrics. That is cost. It's also smaller. What if the comparison of routing metrics fails? Look in this picture. The above two are 10. The following two are 1. What if the following two are also 10? This leads to the next question. Data going to the same destination. Two roads are the same. Inside OSPF, cost is calculated based on bandwidth. Inside Cisco, is 10 to the 8th power divided by the bandwidth. Then the result is the cost value. Theoretically, the larger the bandwidth, the smaller the cost value. This is a very good path. Now cost is equal to 10. It means that the cost is greater. Represents the lower bandwidth of the path above. We want to choose the path with large bandwidth. So OSPF route selection is completely correct. Routing based on bandwidth. For different protocols. It uses different parameters to calculate routing metrics. OSPF based on bandwidth. Well, just like we will talk about an agreement today, called RIP. For such an agreement, it doesn't look at bandwidth. It looks at the hop count. So, different protocols use different parameters to calculate routing metrics. Let's take OSPF as an example. If the current agreement is the same, the cost value is also the same. Then these two routes are added to the table. This is the principle of adding table to the route we are talking about. If the routing metric is consistent, at this time, multiple routes will be added to the table. This is called equal cost routing, also known as overall traffic load sharing. Both of them are equivalent in terms of forwarding capability. But here is a caveat. The cost we are talking about now, the route metric, its comparison can only be compared under the same protocol. Because of different agreements, the way to form the overall route is different. That is, different protocols have different ways to calculate the cost value. So there is no ability to compare. For example, there is now a RIP protocol. Cost is 1. The cost in OSPF is 10. The cost of RIP cannot be compared with the cost of OSPF. because RIP calculates the cost based on the number of hops. OSPF calculates the cost based on the generation width. They are two different protocols in themselves. There's no way to compare them. RIP like a diver. OSPF is like a track athlete. The determinant of a diver's score is splash, speed, beautiful lines, etc. If you get 80 points, a track and field athlete's score determinant is speed, start, sprint, etc. If you get 90 points, then this 80 points and 90 points are not comparable, because the criteria for judging are different. The same goes for routing metrics. RIP is based on hop count. OSPF based on bandwidth. They are not a standard. It is meaningless to compare such parameters. So, cost can only be compared under the same protocol. Let's summarize the table addition principle. There are two additional table principles. The first is to manage the distance. The second is routing metrics. We are looking at these two parameters.